All right, so 1.3 polynomial inequalities. This is in your textbook. If you want to reference for more examples, this would be section 3-2 in that textbook, okay? Homework assignment over this is going to be yet one more worksheet. And then starting tomorrow, we're going to start getting a lot of book assignments moving forward, okay? So sole objective today, when we walk out of here, we should be able to solve and graph a polynomial inequality, all right? So let's go to example 1. I'm actually going to start off with a just a linear inequality to help us kind of visualize how the solution set matches our graphs, okay? So I have two functions up there. F of x in red, it's linear, and then g of x in blue is quadratic, all right? You all know how to solve a linear inequality. That's what we've been doing the last couple days. Choose the color red here. And if I said find when f of x is greater than 0, I can use substitution. F of x is the same as 3x plus 4, right? So I substitute that in. Easy to solve. X is greater than negative 4/3. Okay. All right, now I want you to see how does that solution set match the graph of the function f of x. Obviously, it's the graph of the red line there, okay? And right here would be where negative 4/3 is at. And then this is all of the values for x that are greater than that negative 4/3, yes? So notice how that solution set corresponds to the points on the graph that are above the x-axis, these points right here. Okay? Now, what is true of any point that is above the x-axis? What is true of its y value? It's positive, right? And isn't that what this inequality is asking for? So f of x, it's a fancy way of representing y, right? So we're saying for what values of x are the y's of this function greater than 0? Does that make sense? Okay, so f of x is the same thing as y. When I say find f of x greater than 0, I'm saying find the values of x that make the y of this function greater than 0. Well, for the y to be greater than 0, it's got to be above the x-axis, okay? All right, so that understanding can help us with the quadratic inequality here, which is our first taste of a polynomial inequality. So here's what I often see from students. So they'll substitute the trinomial in there. They'll factor it. X plus 3 times x minus 1. Everything's good up to this point, and then here's what I see from this. I see x plus 3 greater than 0 and x minus 1 greater than 0. Solving those, I get x to be greater than negative 3 and x to be greater than 1. Okay. Well, does that match the parabola that's graphed there in blue and when the graph is above the x-axis? Well, x is greater than negative 3, greater than negative 3 looks like this. Okay, seems to me like all of these points right here that are between negative 3 and 1, their y values are negative, right? Because they're below the x-axis. So this can't be right, okay? Now the second half is actually okay. X is greater than 1. So that would correspond to this section of the curve. That's part of the solution set, right? All of those points have y's that are positive, okay? So the student that takes this approach over here, they're misapplying the property that we use to solve quadratic equations. We use the zero product property. It says if A times B equals 0, then A equals 0 and B equals 0, right? Is that true? If two factors multiply together to be 0, then one or both of the factors have to be 0? Well, it's true for an equation, but is it necessarily true for an inequality? So if A times B is greater than 0, then A has to be greater than 0 and B has to be greater than 0? Can we assume that? No. Couldn't they both be negative? Like a negative times a negative would still result in a positive that's greater than 0. So we don't really have a property like that we can apply in this situation, okay? So instead, we look at the graph here and we say, well, this section of the curve is above the x-axis, so all of its x values have to be part of the solution set. That means x has to be less than -3, or we have this other section of the curve that's above the x-axis whose x values are greater than 1. There's your solution set. Okay? So we need to know when we're above and when we're below the x-axis in order to solve these polynomial inequalities. Okay? And when we go to example 2, I'm going to give you a way we can kind of reason that out without necessarily having to draw the whole graph. Okay? So example 2, we're going to perform what we call a sign analysis. And learning this now is going to serve you very well for the rest of this course, as well as calculus. You do a lot of sign analysis in that course as well. Okay? So I'm going to start with another quadratic inequality. This one's factored for me already. X minus 2 times x plus 1 greater than 0. I'm going to consider the left side like it's a function for a moment that would have a graph associated with it. It would be a parabola. Okay? And I want the zeros of that function. They are 2 and -1. Okay, now, when I plug either of those into the function, the reason we call these zeros is because they would simplify the function to 0, right? Would that make this inequality true? 0 greater than 0? No. So these zeros are not going to be part of my solution set, okay? What I'm going to do is I'm going to draw a horizontal number line here. This represents our x-axis, and I'm going to put in open point at -1 and an open point at 2, since these are not actually part of the solution set. And this divides the number line into 3 intervals. Okay. What I'm going to do is pick a number out of each of those intervals. I'm going to plug it into the function we created in step 1 to see, do I get a result that's positive or do I get a result that's negative? Okay. So in the leftmost interval, I'm going to pick, we'll call it a test value of -2. Okay. So I'm going to evaluate this function at -2. -2 minus 2 would be -4. -2 plus 1 would be -1. So you'd have -4 times -1, which is +4, right? Now, I don't even really care about the full result there. I just care about the fact that this is a positive number. Okay? So going back to my number line there, in this left interval, I'm going to put a plus sign. Okay? Now, a plus sign means that all of the points that are in that interval are where? Above the x-axis. So all of these points are doing this. Okay? Can you agree the point negative 2, 4 would have to be above the x-axis, right? Okay, now I repeat the process with the test value in the middle interval. I probably would just choose 0 here. Okay, so f of 0, that would be negative 2 times 1, or negative 2. And again, what I care about most is that it's negative. I'll put a minus sign there, meaning that all points that are in that interval are below the x-axis. And then we pick one final value out of the rightmost interval. I'd probably choose 3. Plugging that into the function, it'll produce 1 times a 4, so another 4, which is positive again. So I put a plus sign there. And again, that means I'm above the x-axis. Okay. All right, so now we're ready to solve the inequality. So we set the left side equal to f of x. So we could now think of this inequality as f of x is greater than 0. For this to be a true statement, does f need to be positive or does it need to be negative? It's got to be positive, right? A positive will always be greater than 0. So I look at my sign analysis there. It looks like I am positive in 2 intervals. Okay, so I'm going to say my solution set is negative infinity to negative 1, non-inclusive, union 2 to infinity. Questions? All right, let's do another one. Okay, another quadratic inequality. It's just this one's not factored. Okay, so first thing we'll do, move everything to one side. And we will factor it so that we can get the zeros. It'll be x minus 3 times x minus 1 less than or equal to 0. The zeros would be positive 3 and positive 1. Would those values make this inequality true? This time, yes, right? Why? Because it's less than or equal to this time, right? Again, the reason we call these zeros is because when we plug them into this trinomial, we will get a 0 out for y. And 0 is less than or equal to 0, right? So when I make my number line for my sign analysis, put my 1, I put my 3. This time I can put solid points at the 1 and the 3. They're part of the solution set. Okay. I'm going to pick a couple test values. I'd probably choose 0 for the left interval, 2 for the middle, and then 4 for the right interval. Okay, now let me show you a slightly different way you can get your sign values here. Again, I don't really care about the final result of the test value. I just care whether it's positive or whether it's negative, okay? So think of it this way. If I were to put 0 into this first factor, it would make it negative, right? So I'm going to put a little negative sign down here. If I were to put 0 into the second factor, it's still going to be negative. What's a negative times a negative always? A positive. Okay. Now in the middle interval, if I were to plug a 2 in to the first factor, I'm going to be negative. But if I plug it into the second factor, I'm positive. What's a negative times a positive? It's another negative. Okay. And then if I were to plug 4 into either of these factors, I'm positive for both, right? So I'd have a positive times a positive, which of course is always a positive. All right, so this is another quadratic. It's another parabola that's doing this. It's opening up. Okay, now look at the inequality, the direction of the inequality. We're less than or equal to 0. For this to be a true statement, do I want this left side to simplify to a positive value or a negative value? Need it to be a negative this time, right? So my solution is from that middle interval. So any value between 1 and 3 inclusive on each side will make this inequality true. Feeling good? All right, example 4. This is a cubic polynomial inequality now. I've got, move everything to one side, x cubed minus 9x less than or equal to 0. I got to find the zeros, so I need to do some factoring. What can I do to factor first? Factor out the x. Now what? Yeah, somebody said difference of squares, right? And yeah, that's x plus 3, x minus 3. So how many zeros do we now have? There's 3 of them, right? What are they? 0, 3, and negative 3. Good. It's a cubic. Cubics should have up to 3 zeros that are real. Okay, so for your sign analysis, negative 3, 0, and 3. When you make this sign analysis, you don't have to get like super, accurate with your labeling and everything. Just draw a number line, put the 3 values on there, and then pick some test values, right? So left interval, negative 4, be my test value. Okay, so I have to plug that negative 4 into all 3 of these factors, right? So obviously if I plug it in for x, it's going to stay negative. If I plug it in negative 4 plus 3, that's still going to be negative. And then negative 4 minus 3, negative. When you multiply 3 negatives together, what's the result? Still negative. Okay. How about I do a negative 1 out of the second interval here? It's going to make the first factor negative, the second factor positive, and then negative. Negative times a positive times a negative? Positive. Third interval, I'll choose 1. See, I'll get a positive, and a negative. Those will result altogether in a negative y value. And then in the last interval, we can just choose 4. That would give me 3 positives, right? Which, of course, will result in a positive. Okay, so kind of rough sketch of the graph, at least in terms of the x-axis. Negative means below. Positive means above. Negative again below. Positive above. Recall from Algebra 2, that's typically what a cubic graph will look like, right? Okay, now the zeros themselves, I didn't consider that. Are they part of the solution set? Negative 3, 0, and 3. Are those part of the solution set? Absolutely. Because we have 0 included in the inequality. And then is it the positive intervals or the negative intervals that are going to make this inequality true? the negatives if we're less than or equal to 0, right? So we're going to choose here and here. So our solution is going to be negative infinity to negative 3 inclusive, union 0 to 3 inclusive. All right, let's do one more. Here's another cubic, but the factoring's a little different on it. Move everything to one side. For you to use a sign analysis, you always got to be, one side's got to be a 0. Okay. How would we factor this guy? Okay. So you want to like rearrange terms?
Yeah, because you can make x to the third minus 9x and cube. You can factor out x.
Okay.
Make it 0.
I like the idea. You technically don't need to rearrange though. Okay.
You could factor the x squared out of the x cubed plus 5x squared, and then factor out the 9 from the x minus 45, and then they'll both be multiplied by x plus 5.
Very good. What technique are we using either way? Grouping. It's called grouping, right? Grouping. Very good. So, yeah, we could just leave this as is. I'll just group the first two together and the last two. The first two have an x squared in common. So I pull that out. I'm left with an x plus 5. And then the final two, what do negative 9x and negative 45 have in common? Negative 9. So you got to pull minus 9 out, and you're left with x plus 5. And it's not a coincidence that these are the same. We need them to be the same for this technique to work. Essentially what we have at this point is we've got a common factor of x plus 5 that we can factor out and make this into x squared minus 9 times that common factor of x plus 5. Yeah, and then you can factor one more time to x plus 3, x minus 3, x plus 5 greater than 0. And now we got our zeros, right? They're negative 3, 3, and negative 5. Okay, once we're here, it's pretty much the same as the previous example. Are the zeros themselves part of this solution set? Not this time. Zero's not included, right? So we'll put open circles there and then pick a test value in each interval. I'd probably do a negative 6 here. That's, if I plug negative 6 into the first factor, I'd get a negative. Into the second factor, a negative, and into the third factor, a negative. 3 negatives multiplied to a negative. Okay. Then I pick, how about negative 4 here? That's going to give me a negative, and a positive. So multiply those together, you get a positive. Let's do 0 next. Positive, negative, positive, multiplies to a negative. And then 4, that'll give me 3 positives. Which intervals do we want to solve the inequality? Positives or the negatives? Yeah, if we're greater than 0, we need to be positive. So we're going to pick these two intervals right here. Okay, so we're not including the zeros themselves, we said. So make sure you count for that in your notation.